Okay, I think we are recording and sort of like ready and stuff. All right. So I could like change that. Oh, that's wrong. Okay, we're just gonna deal with this. So how's it going today? No one's here yet, so I'm just gonna be talking until that happens. Today we are going to be either covering limits at infinity, L'Hopital's rule, or I guess I like don't have to like share my screen list. Yeah, limits at infinity, L'Hopital's rule, or more specific, or what's it called? Optimization problems. I think I did related rates earlier. I wasn't supposed to do that, but you know that's okay. So yeah, that's sort of what we're like figuring out today. This is really weird. Okay. So yeah, I don't know which one to start out with. L'Hopital's was the most recent. So I might just go over those problems. Although I could do like one of each to start. I guess that sounds good. I might start with like limits to infinity first. Okay. So main idea with like limits to infinity. Oh, okay. I gotta like share my screen. Hopefully this is able to be seen. So the main idea with like limits at infinity is that as you have, so you have kind of function, f of x comes in from somewhere and then it kind of does this and there's like a dotted line and it never touches this dotted line out. It's like this. So that idea, I don't know how well you can like see that. That is our horizontal asymptote. So sort of to define this would be like, say you are taking the limit of f of x. Oh, I literally don't know my notation. My bad. Lim of f of x as x approaches infinity, because x is always going like way over this way, equals that. Cool. Now this is different from our normal asymptotes, which might be something like this, right? Where this might be like a or something. X equals a for like h of x, where the limit of x as it approaches a, h of x, equals infinity. So in this one, you plug in infinity and get out a number, and that tells you your horizontal asymptote. In this one, you plug in a number and get an infinity out, and that tells you that you have a vertical asymptote right here, right? So what happens if we take some function, plug in infinity, and get infinity out? Well, yeah, that looks fine. G of x, actually I can just do, this is just x. This is just y equals x. So I guess I can write it as like g of x. Say g of x, we have limit as x of x as x. Actually, I'll do x squared, just so it's like slightly different. Okay, x squared, infinity. Well, in this case, it's going to be g of x. X squared can just be an example. So to compute this, you're sort of, or to get this, solve this, whatever. You're sort of like plugging in infinity into x here. And so if you're getting a really big number infinity and you're squaring that, that's also going to be a really big number infinity, right? So this is just like, this isn't really anything. It's like, there's not like a like an asymptote. or anything. It's just like, okay, the limit to x equals infinity here is just going to be infinity. Right? Whereas the x goes to like negative infinity, that might be like still infinity, right? Because it's going to go to positive infinity. Whereas for something like x cubed, x goes to negative infinity, x cubed will be negative infinity, right? Because it's going down. Yeah. Okay. So what if, so we've covered 3 cases sort of. So one where we plug in infinity and get a number out. One where we plug in a number and get infinity out of it. One where we plug in infinity and get infinity out of it. So what about just plugging in a number and getting a number out of it? Well, this is exactly what we sort of like always been dealing with. Okay. So I would say this is like, I don't know, t of x. So I have t of x when x approaches a equals L. Well, that just means that either there's a removable discontinuity here, or it's defined there, right? So to tell that, you can just plug in a for x in t of x, and if you get something out of it, then you're good. You know that it's not a removable discontinuity; it's continuous there, so you're all good. But this sort of is a little bit different from what we've had in the past, where it's you plug in this number and you can get a number out of it, and that's just the normal limits that we've been dealing with. So it's sort of like draw a little table for this. You want to do like output here, like input over here. Sort of like think about it like this. Let's say we plug in a x equals a, like x approaches a or something, or like x approaches positive. X approaches, positive or negative infinity. And then for output, what can we get? We can get L or, again, positive or negative infinity. Okay. So based upon what we've done up here, let's try to fill in some of this table a little bit. So we have X. So let's start with this input. We put in a number, get out a number. Well, our output's just going to be, that number, as we sort of said. So it's nothing special, it's just L, right? It's just gonna be, it's like, it basically means like, oh, we have like a point, right? It's just like a set of points. So instead of like L, I'm thinking it's more just like, just like a point sort of, it's like that. Or it's like this. Because it'll either be, again, that, or there could be like a removable discontinuity there, or it's just a circle. Okay, so what if we plug in A and get an infinity out? Well, we already kind of decided that if you plug in A and go to infinity, that means we have a vertical asymptote, right? As it's seen right here. Okay, so what about the other input? What if x goes to a positive or negative infinity? Well, right here, we can see that that's where we get our horizontal asymptote when we get out at just a regular number. So that'll be like HA, right? Then if we plug in positive, negative infinity, and get out positive or negative infinity right here, that's just infinity itself. That's just another infinity, right? Because it just keeps going up in this direction, or keeps going up in this direction, or this direction, or this direction, right? So this table over here is sort of a good little cheat sheet for when you're sort of trying to calculate these and remember how to specifically calculate, okay? Where are the horizontal asymptotes, where are the vertical asymptotes, things like that. So, something to consider. Sort of going into like an actual problem now. I'm not going to really do much with like calculating vertical asymptotes, but I just want to do like a little example for how to do some kind of horizontal asymptote, or at least, yeah. Just find like the limits to infinity. So it's not really like dealing with specifically horizontal asymptotes right now, but I'm just gonna like write out a limit statement. We're just gonna like solve plus minus infinity. I guess we'll just do plus. Right. Let's see, 5x plus 3 is 4. So from sort of like looking at it right now, it looks already pretty easy to sort of figure out. X4 is much bigger of a term and grows much faster than X does. And because it's going to infinity, it's going to dominate the top. Which, so if you have this huge number over here, and like it's still a big number, but not as big, then this is going to grow faster than this one. So the denominator will be larger than the numerator. And so it will go to 0 because some, like huge number over like super small is going to go to, it's like basically 0, right? But it's sort of like more like mathematically calculated. The way I like to think of these things is you keep the limit statement. And I like to think of it as taking out the biggest term of X out of each sort of term. I guess it's the biggest, what's the word? Biggest exponent of X, I guess that's the way to say it, out of each term in like both the numerator and denominator, and then putting them as a fraction over each other, sort of. So on the top, I would take out an X, right? Because X is the biggest, so X, 5. And it's very similar to what Bradshaw does, except he sort of just divides by X, whereas I like to sort of visualize it a little bit better. Take it out. So take the X out of the 5, you gotta take an X out of the 3. So that's gonna get you 3 over X, right? Because then if you distribute back, that's gonna be 5X, that's just gonna be 3. Over, then you take out X to the 4th here. 1 plus 4 over X to the 3rd, because there's already X there. This will be 8 over X to the 4th, right? Okay. So I cannot draw infinity signs. And so what you have here is you sort of simplify it a little bit. 5 plus 3 over X. 1 plus 4 over X cubed plus X4. Right? So I took this X and X to the 4th and I simplified it to 1 X cubed. And from here you can pretty much like plug in your infinity sign. So by that I mean, okay, X to the 3rd is huge and 1 is like not that big. So you know that's going to go to 0 times, let's see this fraction, 5 plus 3 over X. X is huge, 3 is not. So you know that's going to be 0. This should be just 5 plus 0, right? Because 5 doesn't change. Over 1 plus 0 and 0 again. And yeah, you can make this like, 0 times 5 over 1. That's just going to be 0. So we sort of basically could tell, from here, okay, this is bigger than that. This term is bigger. This exponent down here is bigger than this. This grows bigger than that. Therefore, the bottom term is going to dominate. So you can sort of like just simplify it that way a little bit quicker, if that makes sense. So yeah, that's a good example of like sort of like a pretty low level basic way to do one of those. And so if you had these like switched, it'd be the exact same process, except like this X3 would be on the top, right? And there would just be like a 1 on the bottom. And so that would go to infinity instead, because that X cubed would like just shoot up like really high. And would basically just take the entire, like all of the rest of the terms to infinity, right? Hopefully that makes sense. Okay, I want to do another quick example. Showcasing these things. Okay, I'm actually going to do an example sort of combining this idea of horizontal and vertical asymptotes with like limit statements as well. So say I have f of x equals 2x squared plus 3x minus 2 over x squared minus x minus 6. Okay. Now I want to find of this function, find HAs, VAs. So I want to find the horizontal asymptotes and vertical asymptotes. Okay. So for horizontal asymptotes, we can sort of like consult our little table right here. We know that we're looking to plug in for the limit statement at, like an infinity sign, so whatever. So we want to take a limit as x goes to infinity, and we're looking to get like a real number value out of that. That's not infinity, right? Okay. So let's just sort of do that. So limit as x goes to infinity, let's say. And I'll tell you that it doesn't really matter which one you do, because these are both x squared. So even if it was to negative infinity, it would just become positive. But when you're doing like when you're doing dealing with something where the largest exponent, like x term, is like 3 or any other odd number, that's when you're going to have to do separate limit statements for x goes to infinity or x goes to negative infinity. Just something to keep in mind for the future. I'll do like both at the same time, sort of, because it doesn't really matter. So write it out again. I know like writing out all these like fractions and like limit statements is really tedious, but it really makes it easier to grade and just sort of follow along your work as well. So the first thing that we can do here is sort of do something similar to what we did last time, where you would sort of like take these out, right? So you can factor out that x squared. So x squared, so just be 2 plus 3 over x minus 2 over x squared, right? Over another x squared. Be a 1 minus 1 over x minus 6 over x squared. So these x squares would cancel out, right? So we don't really need to worry about those. And all of these would go to 0 because it's x, which is going to infinity or negative infinity, getting really big, whereas the top is really small. So it doesn't really matter. So if this was like a cube, though, that's when like the negative infinity would matter, because then it would go to negative infinity, right? There's something I like consider. I don't really want to sort of go through it, but if this was like an x cubed instead of an x squared, then this term would dominate, and then it would just follow whatever this would be, and so this would cancel out. You'd be only left with x. If x is going to negative infinity, and you're only worrying about the x, then your limit would be to negative infinity versus just infinity itself. So watch out for that in the future. Okay, so these are all zeros. This cancels out, so we're just left with this 2 and 1, right? So 2 over 1. You don't really have any more x's to. I guess we don't really need to write the limit statement anymore because we're just trying to do this. So for 1, that's 2. So that means that we have as x approaches infinity, we have a horizontal asymptote at y equals 2. So pretty simple. Another way to sort of look at this really quickly, you can just eyeball it. These terms are the same exponentially, and so that means everything else is pretty much irrelevant. And then you only have to look at like the fraction of their coefficients. So this is 2 over 1. It's 2. Just a little bit of a quicker way to do it. So for vertical, okay. So as you can see, we plugged in infinity, got out a real number. Basically, what we did in the chart. L is our 2 here right now. You got a horizontal asymptote at that L value. So now we're looking for a vertical asymptote. So here we're trying to plug in some normal value and get out infinity. Okay. So you might be wondering, okay, how are we gonna find an A value to plug in? Well, normally for functions like this, you want to look at points where your function is not defined, like where you're not allowed to plug in x values, right? Especially for a rational function, right? Because there's this it's in a fractional form. So something we can do here actually is we can factor out both the top and the bottom. of this. So f of x equals, I'm just gonna like write out the factor, but I can like sort of show you. Well, actually I can like run through how I would do it. So I know I had to have like a 2x over here. I need to multiply the bottom right, the right side of them by something to get to -2 and 1, or to get to -2. The only way I can do that with integers is by multiplying like -2 and 1 or 1, -2. And you need to figure out which side each of them are on. How should I say this? Honestly, it's a lot of guess and check. I know that I would need a 2x over here. And then x right here. So this is going to be like a 2 or 1. It's going to be a 2 or 1. I have this as a 2 here. And that would, I mean, I don't know. I mean, I like, sorry, it's like harder to like go through my thought process if when I can already like see it. How should I explain this? Yeah, I'm just gonna write it out, you know, it's fine. Okay. So as you can see, like that becomes -2. If you multiply these two together, that becomes 2x squared. Multiply these together, that's 4x, and that becomes -x, and then 4x plus -x is just 3x. So it works. This bottom one though, it's a bit easier to write. This is a -6. That means you either multiply 2 by -3 or -3 by 2. Because this is a -x in the middle, I know that I want my negative term to be bigger than my positive term, or farther away from 0, I guess. Because when you add them together, then it'll still be negative. So I would want it to be just x minus 3, x plus 2. So -6, x squared, -3, 2x, -3x, 2x, -3x plus 2x is just -x. So that works out. You might notice, okay, we have something that cancels right here, right? So that's just 2x minus 1, x minus 3. Cool. So when we sort of are looking at these at first, these are both like, we know that like, you know, if we know that neither of these can be equal to 0, right? Because if these are either x, either of like these terms end up being 0, that means the bottom's going to be 0, and we can't have that. So we know that sort of the points we're trying to like avoid, build our limits even around, are at what should I say? Either x equals 3 or x equals -2, right? But since we canceled these out, that's not really like a possible vertical asymptote anymore. So we don't really need to worry about it. So now we're only dealing with this. So remember to like always sort of like cancel these terms out after you factor. So oh wait, shoot. Okay, wait. Actually, sorry, I explained that poorly. Okay. So let me rewind a little bit. Once you have this factored form, you know that your limits that you want to take they are from this. So this bottom will tell you that your possible VAs at x equals 3, x equals -2, right? Because it's wherever x equals 0, wherever this bottom term is going to be 0. And so those are the points where you want to plug your limit into, where you want your limit, your like x to go approach, right? So we do limit as x approaches -2, for example. Let's say 2x minus 1, x plus 2, x minus 3, x plus 2. These would cancel. And we can't just plug it in normally because then this would be 0 on the bottom. So that's why we had to do some like little algebra first. Minus 3. From here, we can basically just plug in because we know this bottom isn't going to be 0. So 2, -2, minus 1 over -2 minus 3. And we know that's some number. It's just 1. So that's -4 minus 1 is -5. And then -2 minus 3 is -5 as well. So that's just equals to 1. Right up here. 1. Cool. So what does this tell us? So we got our limit statement. If you remember, I mean, we just plugged in a normal number and got out a normal number again. Which that doesn't give us our vertical asymptote, right? We're looking for a limit that produces an output to infinity, right? So that's no good. That's no good. However, if we do a limit statement as x approaches 3, and this is from the positive side, or I guess you might be able to do negative side and then get like negative infinity, but let's just say we're doing it from the positive side for now. To simplify, I'll just start here. So if you plug it in from the positive side, that means x is going to be just barely bigger than 3, right? So it's going to be like a really, really, really small number. So like, right? And then this is going to be like 6. Or it's going to be like 5. So it would be like 5 over super small. If you have like some number over infinitesimally small number, that gets you that infinity, right? Small positive number. Because if you're plugging in like 3.000001 minus 3, then this is what you get. Whereas if you did x3 minus 1 minus 3, then this is going to be like 2.99999 something, which would get you a negative version of this. Small negative. Get you that. Get you that negative infinity. So what this is telling us is that it sort of looks like this. So if you go our graph, so say this is 3. If we go to 3 in for f of x, from the right side, we're getting this asymptote that's going to positive infinity. Whereas we come from the left side this way. Cool. And then from up above, we know we have this horizontal asymptote at y equals 2, right? Well, okay, I drew this poorly. So pretend this goes to like here. And that this is like 2. So I can guarantee you that that's what the graph looks like. Sorry, I didn't put it. So sort of like, you know, it never passes 3, and then it sort of starts from the other side, from the top, it never passes under 2. So that's sort of what that graph will look like. And I wouldn't be surprised if that sort of like shows up in your future homework and stuff. The next thing I want to do is I'll do I think did I do an optimization sort of already in the past? Let me like double check, because I don't want to like do optimization again if I've already done one in the past, unless people specifically ask me to do it. Okay, I haven't. So I can do an optimization problem really quickly, and then I'll touch on L'Hopital. I think this is good. So I'm gonna try to run through it fast. Box has square base. So this is square base. Okay, I'll just write it out. Square base and open top. Open top with a volume of 30 meters cubed. The materials to make the box each costs like money, each side of the box. So the materials for the bottom part of the box is going to be, so mats for bottom. That's what? It's 5 per meter squared. Sides, 3. We want to find dimensions of the box with minimum cost. So in each optimization problem, you're always given a constraint, right? Because if we didn't have this constraint, then we could like write like a equation for sort of like drawing this out, this like problem out, but we wouldn't really know what to sort of base it off of. So to sort of draw it out a little bit, I can try to draw my little 3D box here. Oh shoot. Sorry, I'm not the greatest drawer. That wasn't terrible. So say this is X, this is Y, this is open. This top is open, right? Okay. So we need a function for the cost. So this cost can be like any number, basically. We're trying to make it super small, right? So what can we say about how, well, I guess I'm just like talking to myself at this point. So we want to sort of use these values that we're given to sort of plug into here. To sort of like create an equation for the cost, right? So if we know that the bottom has dimensions x by x, that means the area is going to be x squared, and then it's $5 per meter squared. So we can write it out like 5x squared. And then for the sides, there are 4 sides, right? And that's going to be 3xy because each side has an area of x times y, and then times that's the cost again, right? So that's like 12xy. Our constraint is this volume equals 30, right? What's our volume of this box? Well, it's just all the different dimensions of it multiplied by each other, right? So we get x squared y equals 30. Okay. From here, so this is sort of like the general like method to go through when you're dealing with constraints. You want to write out some equation that you're going to plug stuff back into for finding out, the minimum cost or like the minimum volume or minimum area, whatever it is. Because your volume and like area equations for like dealing with like some kind of like fence thing could be different, right? And then with your constraint, you set up the equation for the constraint and then solve for y, right? This is just always what you do. You always solve for y in this case. Or get it to a point where like you have it as a function of just x. So if you can plug in something for y, and then sort of like equals, some value, that also works. But normally speaking, when you sort of have this y, you don't have anything to really plug into it. It's like its own separate thing. That's when you want to set it equal to each other. Equal to like some function of x, right? And so once you have it equal to y, that's when you can plug it in back into here, right? And at that point, then everything in here is x. Yeah, I think I spoke a little bit earlier. I think I got ahead of myself. So normally, whenever you have this sort of like constraint equation, like this isn't your constraint equation, this is your like cost equation or like trying to find like a minimum area or minimum volume of whatever the box is. It depends on whatever the situation is. You always want to be able to plug something in for y in terms of x so that you don't have to worry about it. And then at that point, c basically just becomes some function where it's like c of x, right? Sorry if that like is poorly drawn. So if we just write it out again, 12 12x, right? 12x, and then that's time multiplied by our y value, which is 30 over x squared, right? Which is just 5x squared, what is it? Plus 360, x to the negative 1. So right now, we basically have a way to determine, depending on whatever x is, as long, given some kind of value x, we can determine the cost of it. And so that like it's sort of like moves up and down, this function, depending on sort of what x value that we plug in, right? And we know that this y is sort of like just dependent on this x value because of our constraint. And so from here, once we plug in our y value and all x's, we want to find sort of how this cost sort of fluctuates, and we want to see where its maximum and minimum points are because we're looking for that minimum cost, right? So we take the derivative of it. This derivative is 10x minus 360x to the negative second. And you set it equal to 0 because that's where the slope is going to be flat in this point. So that's when it's going to be that y value of the derivative is going to hit 0. And then at this point, you basically just just solve for x pretty much. So from here on out, you can sort of write it out as 360 x squared 0, multiply everything by x squared, because you're allowed to multiply everything by x squared because that's just fine. So 10x cubed minus 360 equals 0. I can just add it over. 360, I get 3 cubed equals 36. And then x equals square root of 36, cube root of 36. Cool. Which is about 3.30. Awesome. So now we have a point where it's either a maximum or a minimum, and we don't know which one yet, right? So we need to sort of do one of those little like sign charts just to make sure that we have a minimum and not a maximum, because it could either be a slope like here, or it could be like a slope like here. So starting at 0, it's going to be at our root 30 or cube root 36. Because you can't have a negative length, because this is what our length is, right? For our box up here. It's our root 36, cube root 36. So basically, we need to find out on which side of it is it positive, which side is it negative, or maybe it's positive and negative on both. So the equation that we're sort of like basing this off of is just going to be ripped straight from what we have here, which is our derivative, right? So actually, no, it's going to be from our original. Sorry, it's going to be from our original, I believe. Hold on. Yeah. Sorry, I'm just trying to like think through this. Yeah, you would oh no, it's gonna you plug it into the derivative, to the derivative of the function, because then it tells you whether or not it's like increasing up here or decreasing. Okay, that makes sense. Okay, so you plug it back into it's like what? You can plug it back into 10x cubed minus 360. And so I don't know what cube root of 36 is. I can calculate that. Oh wait, yes I do. It's 3.30. So you could plug in like 3 or something. And here 3 cubed is 27. 27 times 10 is 270. 270 minus 360 is negative. So that means that on the left side of this, between 0 and 3.330, it's going to be negative, or the function will be decreasing. And then if you plug in like 4 or something, 4 cubed is 64, 10 times 64 is 640. That's going to be positive. So that's like this. So that means we have our minimum value. Cool. So we know this is a minimum, which is awesome. So that means that we know that we have a value for x for which our cost is at minimum. So now we just need to find a y value for it, which luckily we can do given our constraint, right? So we basically just plug it right back in. So we take our cube root 36 and plug it in for our x value from up here. And then this is about 2.75. And I mean, those are the dimensions. So x, so it would be x, it would be like what? 3.30 by 3.30 by 2.75, right? And that's your answer. And so if you wanted to find out what that actual minimum cost was, you could just plug it back in right here. And that would get you some number. But yeah, that's sort of how you do it. So optimization problems in general, you're going to only be working with 2 different sort of equations. Your first one is generally going to model what you're trying to find the actual minimum of. The second one uses the constraint. From the constraint, you plug it back into the original thing. You take the derivative of this original one. You set it equal to 0, and then you just basically it's like a min-max problem from there on out. So I can go over other examples in the future, but that's sort of just one general way to do it. So it's basically just being clever with trying to create these different functions for the specific what's the word, for like the event or scenario or situation, and then just like doing some math and then figuring it out from there. Okay, cool. So I have like 15 minutes left. I'm going to go over L'Hopital. Okay. So there's a lot of examples here. L'Hopital's problems are really long. I'm probably only going to go over one longer one. I feel like in general, like how you sort of do it isn't that bad. I think one thing to consider is being able to recognize all the different indeterminate forms and what's like an indeterminate form versus something that's just like 0 or infinity. So like 0 times infinity is, wow, that's awful. 0 times infinity is indeterminate, even though it seems like it should be in that form, which is kind of a bummer. But normally, if you're ever doing limits and you run into something where it's like 0 times infinity, and this will really only happen when actually no, that's not true. Yeah. So you normally when you run into something any kind of indeterminate form, you can turn it into something for L'Hopital where we want 0 over 0 or infinity over infinity, right? So take a lim x goes to infinity of x e to the negative x. So if we just plug this in, do like, our lim x goes to infinity, x times lim x goes to infinity in negative x. This goes to regular old infinity. This goes to 0. because e to the negative x is like 1 over e to the x. And e to the x to infinity is really big, infinity, and 1 over infinity would basically go to 0. So it goes to 0. Or you can think of it as, so you have your function, e to the x. You're plugging in, you're going to infinity, but you're going to negative infinity for the function e to the x, right? So you're basically going this direction in it, which goes to 0. So that's another way to sort of think about it. Oh, that's how I like to do it. Okay. So we have this, but we're like, shoot, like what are we supposed to do? We have an infinity times 0. We can't like do L'Hopital's immediately. Well, you can convert it to a L'Hopital. Convert to LH. So you can basically do what I did right up here. The limit x approaches infinity, x over e to the x, because it's like a negative exponent here, right? So you can just move it down. If you do this, we get this whole negative infinity and then like infinity thing, which is good because if if x goes to infinity, okay, e to the x also goes to infinity. So that means that we can use L'Hopital's on this one, which means h, you take the derivative of both the top and bottom parts of the fraction separately. Again, this is not quotient rule stuff. You take the derivative of the top separately from the bottom, and vice versa. So you take the derivative of the top, which is just 1. Bottom is e to the x. And from here, it's a pretty simple just limit problem. E to the x goes to infinity. So since the bottom is going to infinity, it's going to be 0. So that's a really quick problem. I have more complicated ones. I know you probably have sort of seen the whole thing where you sort of like take the limit and set it equal to L, and then you take like the natural log of both sides, and that allows you to like do some fancy stuff. I can maybe do that when people are here, just because I feel like if I just do it, no one's gonna understand it, and it'll be like rough. So I think I'm just gonna end the session here, just because no one's here. Hope you guys sort of learn something about all these different things. I guess we can like write out some more indeterminate forms just so that you guys can sort of see what those are like. So 0, 0, 0 over 0, that is indeterminate. But that's one of the forms that we can use L'Hopital's for. So that's why we like it. Infinity over infinity, again, we like this. It's indeterminate, but we can use L'Hopital's on it. Indeterminate basically means we don't really know what it is. Like 0 divided by 0 times, like we're not really sure what that is. We can't really divide by 0. It's not, it's different from being just like undefined, I think. It's sort of weird. You can like Google that if you're more interested in it. Some other ones that we don't like as much because we can't use L'Hopital's. 0 times infinity. That's what I look into. Yep. Infinity minus infinity. Which I know seems counterintuitive, but remember, infinity is not a number, it's more like an idea. So if this like continuously like going really, really big and subtracting by also something that's continuously going really, really big, you can't really like pinpoint, okay, these are gonna both subtract each other at the exact same time, go to the exact same point. Unfortunately, you can't really like look like that too easily. Another weird one, infinity to 0, power 0. And again, this is sort of called back to the whole like infinity is not a number. So like, like 5 to the 0th power is like 1. Anything, any integer or number in R, which is like a set of real numbers, to the power of 0 is just 1, but infinity is not that. So it's kind of a weird thing. Like infinity is not a number, so it doesn't really like work that easily, sadly. And then the last one is 1 to the power of infinity. So again, like you'd think like 1 to the power of anything is just 1. But again, because it's like infinity, it's not a number, we can't really like say that that's true, which is kind of weird. And there's some other ones that I'm probably missing that I'd look into. So just be careful if you ever like run into something like this when you're doing your limits. Normally, if you do some kind of like limit to infinity, you always need to be looking out for L'Hopital. It can be very, very useful, just in general. So yeah, I just watch out for it and make sure not to like pretend like accidentally I think that these go to like 1 or this goes to 0, something like that, or this goes to 0, stuff like that. So yeah, if you want to look into like why these are sort of indeterminate, you can just Google them. There are probably some good videos on YouTube. So yeah, okay, I'm gonna end it here. Thank you so much. I hope you learned something. Have a good